Welcome to our third Science Breakfast seminar for the year, and it's my great pleasure to welcome everyone here. It's a beautiful sunny day. Let me begin by acknowledging the traditional custodians of the land on which we're gathered today, the Gadigal people of the Eora Nation, and pay my respects to their elders past, present and emerging. It's my great pleasure today to welcome one of our most famous quantum scientists in New South Wales, Andrew Dzurak. I've known Andrew, I think, for about a decade or so, off and on, in different types of roles. Andrew has really been one of the pioneers in quantum computing, and it's great to see, I think in the last 5 years, Andrew really set sail all by himself and really create and establish some fantastic technology, and also being a long way down the path for commercializing it as well, which I think is really what we're looking forward to in the quantum area. Andrew is a professor at UNSW in the quantum area, but more importantly, he's the CEO and founder of the company Diraq, which is developing quantum technologies based on conventional silicon processing technologies. And I think this is the big advantage of what Andrew is putting forward, is the fact that we can use existing silicon foundry techniques to build quantum computers. And I think that's fantastic. Andrew and his team are aiming to scale qubits on a single chip into the many millions. So the sorts of things that we see on conventional chips, but applied to quantum chips. And this will enable practically powerful and low-cost quantum computing. Andrew is very well known in my office. We established a quantum computing fund, I think back in 2023. I lose track of time these days. And he was one of the early recipients, and we're very proud to be one of the early funders in Diraq. Having said that, this is exactly the kind of outcome we like, because we put a little bit of money in, and Andrew has gone on to raise an additional $142 million US. That's exactly the kind of scaling that we like to see from our investments. So it's fantastic that you've been able to do that, Andrew. And I think we should all actually congratulate him on getting such success in a short space of time. So it's taken a long time, I know, 25 years, 60 patents, 11 patent families and things like that, but I hope we're going to hear a lot about that today, and also what's really going to be happening in the quantum field in the next decade and how it's really going to commercialize in Australia. Welcome, Andrew.
Well, thank you very much, Hugh. Is this on okay? Hearing me? Thank you, Hugh, for that very, very kind introduction. And I want to really acknowledge Hugh for everything you've done for the ecosystem here, not just for quantum computing, but also for the entire science and engineering ecosystem. And also I'd like to acknowledge your predecessor, Mary O'Kane, former Chief Scientist and Engineer, because what we've been able to achieve has only been possible because of the amazing ecosystem that we have here from a scientific and engineering perspective, particularly in the quantum computing area. But I should mention that, through the Office of the Chief Scientist and Engineer, and Hugh's continued this funding since Mary O'Kane's day, there's been significant investments into the centres of excellence, such as the Centre of Excellence that I've been a part of for 26 years, Centre for Quantum Computer Technology. And also through the NCRIS facilities, the AMF, National Fabrication Facilities and so on, which have been crucial to help us develop our technologies. And as Hugh mentioned, at a time when we were just getting the company off the ground, the Quantum Computing Commercialisation Fund that Hugh instituted was really, really crucial for us at a time when we really needed that support. So thank you very much, Hugh, and thanks to the New South Wales Government in general. I'm going to talk about our company, but more broadly about quantum computing, what it has to offer. And I'll tell you a little bit about our vision for how it has the opportunity to really be world-changing, but for Australia, to be economy-changing. We think that quantum computing is really, well, we know it is a major strength of Australia. Happens to be a very, very major strength of Sydney, generally. Sydney is one of the hottest centres for quantum computing research anywhere in the world. We've got one of the highest concentrations of outstanding quantum scientists and engineers anywhere. And we have a real opportunity to make a huge global impact and what will be a big economic impact in the country. So let me just get this rolling. So quantum computing, for those, it's great to have a general audience. I know I've been speaking to some people from very diverse backgrounds, and so I will be keeping this pretty high level. I'll show a little bit of technology, but I really want to keep it hopefully at an understandable level for people who are outside the field. At the bottom line is that what quantum computing offers is the ability to harness very, very complicated quantum physics to solve problems that actually can't be solved using existing computing capabilities. And when I say existing computing capabilities, I mean no matter, for some problems, even if you put together all of the computers on the planet, they would still take so many years to solve some of these problems that it becomes infeasible. And for another whole class of problems that I'll talk about in a moment, it's simply, even if you can consider taking those problems on, they would take so long that it's just not worth the economic cost of running, you know, a high-performance high-performance computing center or data center for that long to solve those problems. And it's these problems, and I'll come to them in a moment, that really are just beyond the capabilities of standard computers where quantum computing will make a real difference. This is one obligatory slide about quantum computing and about quantum bits, just to get a bit of terminology right, and also to describe the key differences. So on the left, we've got some very simplified picture of what a standard bit of information is. In our chips in our phones and laptops, bits are stored as digital voltage levels in transistors. So, and in the whole idea of a digital bit is that the voltage level for a 1 is meant to be significantly different to the voltage level for a 0 when measured inside an electronic circuit. And the fact that these two are well separated means that even if there is some electrical interference that causes those levels to jiggle around, they're still well separated, and so that means that we have a very clear, definite 1 or 0. This difference, this ability to resist noise, is often called the good noise margin of digital signals that allows us both to communicate with digital signals but also to compute with it. Now, a quantum bit is a very different thing. So the idea of using, so let me give you an example of quantum bits. Pretty much there are as many different types of quantum bits as there are particles in nature, because any fundamental particle or group of particles could ultimately be used as a quantum bit. It's just that some are a lot better than others. So typically, the type of quantum bits that we use are single electrons. Okay. Other examples, you may have heard of the company PsiQuantum, which is setting up quantum computing facility in Brisbane. They use single photons or single particles of light. Particles of light are actually easy to explain in a quantum sense because for those of you who are used to having polarized glasses, you know that when you turn it around, it goes light or dark, and that's because light is polarized either vertically or horizontally. Okay, and so for a single photon, you can actually define one state as being the vertical polarization and another state as being the horizontal polarization. In the case of electrons inside electronic devices and inside the devices that we use, silicon quantum bits, it turns out that an electron has a property known as its spin. It's a tiny angular momentum. It rotates on an axis and it generates a tiny magnetic field. And you can think of it as a tiny bar magnet where the bar magnet north pole is either pointing up or pointing down. And so this also allows us to define a 1 or a 0 for an electron spin quantum bit. In the case of a photon, it's a 1 or a 0 in terms of the polarization. And there are many other examples of different particles and systems in nature. All right. Now, how does this turn into something useful for calculation? So on the right-hand side, you see an image of a sphere, and one can think of, and this describes the mathematical description of a quantum state on a single quantum particle. Because if we think of the south pole of that sphere as, for example, that electron spin pole pointing downwards, and if we think of the north pole as the spin pointing upwards, then we can think of those as a 0 or a 1, okay? Now, and this is where we bring in quantum mechanics. quantum mechanics, which was developed in the 1920s for the first time, describes the behaviour of particles at their most fundamental level. And quantum mechanics is not something that most of us feel intuitively, because we're not used to looking at things right at the atomic or fundamental particle scale. And there are weird things that happen. So one of the weird things that happens is that it's possible for a single particle to exist in what's called a superposition state. So if we take our electron, it can exist in both the spin down state and the spin up state at the same time. Okay? It turns out that when we look at it or we try to measure what it is, it will always turn out to be down or up. But before we measure it, it can exist in what's called a superposition state. And the mathematical way in which this is represented is by this often called a Bloch sphere, where you can actually get a mixture of the down and up by being somewhere on the latitude here, and then there's another mathematical aspect that gives it another dimension, which is the longitude. Okay, so a single particle actually has a lot more information in it than just the down and the up. And so when we combine that superposition property with another property of fundamental particles, quantum particles, called entanglement, where if we have two separate particles, it turns out that if they were initially interacting and then we move them a long way apart, they still remember, they have a memory of each other, even if they're on the other side, opposite ends of the universe. So these two properties, superposition and entanglement, mean that quantum bits have a lot more information, and when we process with them, we're able to do things that we can't do with classical bits. It turns out, because of that extra information storage capacity, for certain problems, we can actually get exponential speed up. So as we add quantum bits, the processing power grows exponentially with those number of bits rather than linearly or, say, polynomially. Now, that's a great strength of quantum computing, and the concepts for that were first, the idea of using quantum states for doing processing was conceived by a Nobel Prize winner, Richard Feynman. He didn't actually get the Nobel Prize for that, by the way. Pretty amazing that he actually got it for a thing called quantum electrodynamics, but he was just asked to give a lecture on where could computers go, and in the 80s at Caltech, he came up with this idea that you could actually use quantum particles to do computing. Since that time, in the 80s and 90s, there was a lot more development of the idea of using these quantum bits to do powerful computing. Although you have lots of processing power in these quantum systems, the benefits also create a danger for quantum computing. So, as I mentioned, with our classical bit, we have a well-separated 0 and a 1 that is immune to disturbance. But in the case of the quantum bit, if we think of the pointing on the sphere, even a small amount of perturbation will change my quantum state, and that creates errors, and those errors hang around. And so what that means is that if we want to do calculations with quantum bits, we have to protect them from that disturbance. So we have to create it turns out, very complicated error correction codes where we take a large number of physical quantum bits, it could be a large number of electrons, it could be a large number of photons, and we put them together in what's called an error-protected logical qubit. And in that way, we can then do useful calculations with those logical qubits. But the numbers of those physical qubits to make a logical qubit can be very, very large in order to protect those errors. It can actually be in the thousands. And so what that means is if we want to do useful calculations with these quantum bits, we typically need millions of these physical quantum bits to do useful calculations. And the reason I've spent so long explaining that is because that is actually the reason why our company has focused on silicon as the pathway to make these quantum bits. And I'll give you an example of some other technologies and what are some of the challenges that they face in getting to those millions of physical quantum bits that are required to do useful calculations. All right, let's now look at some of those applications. So this slide covers, let's say, 4 of the major classes of problems that are often being looked at now for the applications of quantum computing. I'll start, for example, with the one on the top right, which is discovering new materials. In this case, it's talking about for the energy transition, and I'll come to that in a moment. So one of the aspects of quantum particles that makes them particularly attractive for designing new materials is that when we try to calculate, materials are made, of course, of atoms, and they connect together in a molecular system. In order to calculate the exact state of a molecule, in order to do some, let's say, computer-aided design, if we want to predict the properties of that molecule, it turns out that's a very difficult calculation. And the reason for that is because that molecule is made up of atoms, which are quantum particles, and which have many of these different superposition states. And so because there are so many variables, even for a single atom that's involved in the molecule, as you add more atoms in the molecule, the number of variables blows up exponentially. And so to calculate it becomes a very, very difficult mathematical problem. In fact, a molecule with just 50 atoms, this is similar to the size of our caffeine, one of our favourite molecules in our coffee, right? Caffeine is already at a size where it's right on the borderline of what even the biggest supercomputers on the planet can do an exact calculation of. And so once we get larger molecules, like let's say we were trying to design a super lightweight material, I don't know, to make an aircraft be much more, very, very excellent strength to weight ratio to make aircraft travel more efficient, for example. In order to design that, if those molecules are bigger than 50 atoms, we can't find exact solutions with classical computers. Now, we can find approximate solutions, and in fact, artificial intelligence has allowed us to do some excellent guesses for what might be good molecules, but ultimately we can't do those final calculations. And so this is one of the areas that is really identified as one of the big applications of quantum algorithms when we have quantum computers with the millions of qubits that are able to do those calculations. At the moment, the most powerful quantum computers on the planet, and these involve, for example, superconducting qubits I'll talk about later, which are still only in the hundreds of physical qubits, something like 4 orders of magnitude away from the scale required to do those calculations that I talked about just a moment ago. So coming back to those problems, what are some of those applications? So we can think about designing new materials that could be used to create lighter weight materials. We could think of designing new battery technologies that could make batteries much, much lighter and cheaper to make to allow us to store electrical energy, crucial for the energy transition. Another example that's very often quoted because it is just so important as an energy consumer on the planet is the fixation of nitrogen. So all of the fertilizers that we use today, the vast majority of them are based on ammonia. But the production of ammonia turns out to be very, very energy intensive. Now, if we could find, and it uses a process called the Haber process, if we can find a catalyst that could enable the fixation of nitrogen to make ammonia far more energy efficient, even if we just reduced the energy consumption of that process by 10% or 20%, that's a huge energy saving on the planet. I mean, the Haber process actually takes up a significant number of percent of energy on the planet. Another example we've got here on the top left is drug discovery. This is potentially one of the most exciting applications of quantum computing. Today, we know that in order to develop new pharmaceuticals, it actually costs many, many, many millions of dollars. In fact, it's now approaching tens, in some cases, approaching $100 million for a pharmaceutical company to develop a new drug that could be used for fighting some type of disease. So if, however, we can use quantum computers to very quickly identify candidate molecules that can be used in trials, it means it will significantly reduce the time those trials have to occur, and that lowers costs significantly. This is really one of the most exciting, both from an economic perspective, but also in terms of the benefits for society and the globe in terms of reducing disease. And then on the bottom right, and I'll just give one more example, there are many applications in areas that are, very everyday applications. For example, financial modelling. There are a number of quantum algorithms that show that when you have very complex data sets, again with very many variables, very difficult to calculate on conventional computers, quantum computers can provide very, very quick solutions in comparison. And finally, in the area of logistics, finding the optimal routing to move goods around the world and so on, or scheduling appropriate pathways for deliveries and so on. Turns out that quantum computers can very efficiently solve those sort of route finding problems much, much more efficiently than conventional computers. That problem actually blows up exponentially on conventional computers. So these are some of the areas, and when we add all those up, it turns out that it creates very, very significant benefits in overall revenue. In fact, revenues of order $1 trillion per annum are estimated when we add up all of those applications together, when we have quantum computers that are powerful enough to take those problems on. I've just listed here, there are very many reports that have been done by firms like McKinsey's or BCG. This is one by ICM Limited that collected some of these. And perhaps at the far right, we see the overall potential revenue generation for quantum computing is up in the, say, $1 trillion level. The actual market for quantum computers themselves to sell those and to make them available is already in the targeted in the tens of billions by around about 2040 or so. And there have been similar analyses done here in Australia. The CSIRO report from a couple of years back, this was instituted by then Chief Scientist Kathy Foley, estimated very, very significant revenues from quantum computing available in Australia. From the capabilities that we have here. It projected some billions of dollars from quantum computing by 2045. Our vision at Diraq is to multiply that by at least a factor of 10. We think that this is a massive underestimate of the potential for quantum computing in Australia. And one of the reasons for that is, as I mentioned earlier, we have an incredibly rich ecosystem here in Australia. So I mentioned earlier the Centre for Quantum Computer Technology, Quantum Computing and Communications Technology, that was originally established at UNSW in 2000 by my former mentor, Bob Clark, who went on to become Chief Defence Scientist of Australia, and now led by Professor Michelle Simmons. That centre, which has been running for 26 years, really was one of the great groundbreakers internationally in creating a national focus for quantum computing. So although headquartered at UNSW, had nodes all around Australia, including places like the University of Queensland and the University of Melbourne. And it went through, and it's gone through multiple generations, first as an ARC Special Research Centre, then Centre of Excellence, and then in 2011, another really great Centre of Excellence, the Engineered Quantum Systems, EQUIS, was created. This also generated amazing technology and capability. And in our outstanding universities all around the country, we have an amazing array of quantum talent. We've also, here in Sydney, and again, commend the New South Wales government some years ago for bringing together the 4 research-intensive Sydney universities, UNSW, Sydney, Macquarie University and UTS, to create the Sydney Quantum Academy. And that brought together the talent from those 4 universities together, both to create an overall overarching educational group, but also to build up the ecosystem and help promote startups and communication of this in Australia. So that academy now over 5 years old and still going strong, and it actually then led at a national level to a broader body that was set up last year called Quantum Australia. This was a federal government initiative, and many people here in Sydney have been really instrumental in setting that up, including Professor Steve Bartlett, who's sitting here in the audience, I see. So, and finally, the Australian Quantum Alliance is a sub-body of the Tech Council of Australia, which was brought together all of the companies involved in quantum technology. And I've listed here some of the Australian startup companies, Q-Control, Quantum Brilliance, Silicon Quantum Computing, and a new company, Emergence Quantum, I'll say a few words about in a moment. And it really is a thriving ecosystem. And there are actually many more that are just starting up, smaller startups, both here in Sydney and around the country. So super strong capability here in Australia. Okay, so let's look a little bit at some of the background of quantum computing, of quantum technology, but also of our technology at Diraq. So people, I'm not sure if people are aware, but this year is in fact the UNESCO International Year of Quantum Science and Technology. If you'd like to learn more about some of the activities, please grab that QR code, and Diraq's a proud sponsor of this. And it commemorates the fact that 1925 was really seen as a pivotal year in the development of quantum mechanics. Some of the core concepts were developed and really brought together by three giants in the field, Erwin Schrödinger, who really kicked it all off, and then Erwin Schrödinger from Austria, Werner Heisenberg from Germany, and then Paul Dirac from the United Kingdom. And in fact, Paul Dirac is where inspires the name of our company, Diraq. His father was Swiss, but he was brought up in Bristol. So a bit of a, not sure whether the appropriate pronunciation is Diraq or Dirac. You can take your choice. But Paul Dirac was really a giant. Not only did he come up with some of the core postulates of quantum mechanics, he developed a whole mathematical language to describe how to work and how to calculate quantum systems. Importantly, he also combined quantum mechanics with special relativity for the first time, Einstein's special relativity, to formulate a thing called the Dirac equation. And that Dirac equation predicted the existence of particles at that time had never been discovered, antiparticles. Okay? And it was actually for that he, together with Schrödinger, got the 1933 Nobel Prize. But the other thing that the Dirac equation naturally predicts is the existence of spin of electrons. The fact that there are two possible states of an electron, spin up and spin down, which is the core technology for our company. I want to also acknowledge two other really important scientists much later on, and there's Daniel Loss from Switzerland and David DiVincenzo, an American. David had been working at IBM Research at the time. David's now in Germany at Aachen University. But they conceived of a way to do quantum computing using spins in semiconductor devices. And at the time, the research community was studying a type of semiconductor device known as a quantum dot. This is a device made in semiconductor systems that is, when made very small and then cooled down to low temperatures, the electrons that are trapped in this small electronic device exhibit their quantum properties very clearly. And in fact, in the 1990s, the technology had just reached the point where those quantum dots, it was possible to actually see that you could trap single electrons in those. At the time I was doing my PhD in Cambridge, we were studying these quantum dots. At the time, most of the work was done in a semiconductor system, a compound semiconductor system called gallium arsenide or gallium arsenide, aluminium arsenide. And this was really the technology that was focused on at the time. And it was in that system that Loss and DiVincenzo proposed the idea of using these electrons trapped in these electronic devices and using the spin of those electrons to do computing. That paper from Loss and DiVincenzo was published in 1998 in Physical Review. In the same year, in 1998, in Nature, here in Australia, we had an important paper by a person who was a colleague of mine at UNSW at the time, Bruce Kane. He was an American who was doing a postdoc in the group of Bob Clark that I mentioned before alongside myself. and he conceived of using silicon as a base material. In his case, he looked at using the nuclear spins of phosphorus atoms. And that technology is the technology that Silicon Quantum Computing, the other company I mentioned here, led by Michelle Simmons, is pioneering and taking forward and working to commercialize. What I decided though, I'd been looking at that technology of using nuclear spins and single dopant atoms in silicon, and saw that there was a great potential for a combination of this idea that had come out of this gallium arsenide technology invented by Loss and DiVincenzo, and combining that with some of the benefits of silicon. It turns out that silicon is a fantastic material for doing quantum physics in. And the reason is that we can remove all of the background spins that create the noise that can disturb those fragile quantum bits. It turns out much, much better than you can do in gallium arsenide. And so we began a program actually in the first decade of this century to start to see whether we could make quantum dots in silicon, and in fact, not just in silicon, but in modified silicon MOSFETs, the same type of devices that we use to make transistors. As it turned out, we used some of those first quantum dot devices to, in measurements to read out the state of those phosphorus atoms I talked about before. That actually led to some of the first breakthroughs here in Australia on measuring single atom quantum bits. So there was some work that was published in Nature in 2010 that actually just reached 1,000 citations over the past week or so. That was led by my colleague Andrea Morello, that some of you may know. We used a silicon single quantum dot device to read out the state of this single atom. And Andrea, and then since that time Michelle, have really moved forward with that single atom technology. I was more interested in the readout device, because the beauty of that readout device is it could be made with standard manufacturing in chip foundries. And so that's really what I want to really now talk about, the use of that CMOS technology to make quantum processor chips with millions of qubits in an economical way. So let me now talk a bit about our company Diraq. So we founded it in May 2022. This was done with an initial, actually, I have to correct the number. It is 140 million, but that includes a lot of funding that came in the decade before through research grants and so on. Since we launched the company, we've raised around 50 million US. Still not a bad, still a good multiple, Hugh. I think we'd take it. And a lot of the IP that we developed in the preceding decade has rolled into Diraq, as Hugh mentioned, over 60 patents worldwide. And all of those patents have been backed up by really leading research papers that have been peer-reviewed in journals like Nature and Science. In fact, just today, we have a paper coming out in Nature jointly with Professor David Riley's group from another startup I mentioned earlier, Emergence Quantum. I'll talk a little bit more about the results of that Nature paper later on in the talk. So we now have 50 staff in the company, and we've also incorporated in the United States and in Germany, and we're hiring in the US at the moment and expanding at the moment. Here's a picture of the team outside our labs on the campus of the University of New South Wales. We've got to give a big shout out to UNSW. It's been a great university supporting quantum computing research generally, and it's been a great supporter of Diraq. It's a shareholder in our company, and we utilise one of our labs. We utilise facilities on that campus in many ways, including our own lab, which is in the basement of that building behind the team there. This is a photo taken in December last year. So our core technology, as I've now foreshadowed and Hugh mentioned, is based on using standard silicon chip integration. And what this means is that we can make our quantum chips in standard foundries. And importantly, because the size of our quantum bits are very small, we can get millions of qubits on a single chip, and that means we need just one cryogenic system in order to make make a full-scale quantum computer. I want to say a couple of words about some of the different technologies that are out there. So this slide lists the 5 really leading technology approaches for quantum computing, including silicon. You can see there listed superconducting circuits. This is a technology being pursued by companies like IBM and Google. Trapped ion. These are ions that are trapped in electromagnetic traps in vacuum. Some really huge startups now valued in the billions in the US and Europe. IonQ and Quantinuum working on that technology. Neutral atoms, quite similar to ion traps, except here, rather than having charged ions, you have a neutral atom. These are held in place using interleaved laser beams and laser cooling technology. So ion traps and neutral atoms need a lot of lasers. And then the last one, photonics. This is the technology being taken forward by companies like PsiQuantum and Xanadu from Canada. They use integrated silicon waveguides in order to move photons around, and in this case, the photons and the qubits. So all of these technologies really have led to major companies and many hundreds of millions of dollars of investments up into the billions around the world over the past few years. We view that that a lot of these technologies, I mean, they've been crucial for doing the first demonstrations of quantum computing. And the small-scale quantum computers with tens of qubits, even approaching 100 now, are being employed. But we view them in similar way to the first digital computers. Pictured at the top left there is ENIAC from the 1940s. It was often considered the world's first useful digital computer made using vacuum tube technology. These vacuum tubes, you know, were sort of the size of your hand. Each one was effectively a logic switch. Similar to what is now a silicon transistor that is something like a trillionth of the size. Of course, digital computing really was revolutionized with the invention of the transistor, which could be made increasingly small, so that now on a single square centimeter of silicon, we can include something like 100 billion devices now. And that's really enabled the information technology revolution. And we see the same possibilities and opportunities for using this integrated silicon technology to make billions of qubits on a chip, and that's really the focus of Diraq. And the reason that we can do that is our quantum bits really look very much like standard silicon transistors. So the cartoon at the top shows actually not a bad representation of what a standard silicon transistor looks like. The brown at the bottom is silicon. The black thin layer is an insulator, typically silicon dioxide, and the grey region at the top called the gate is metallic. And that metal oxide semiconductor is the MOS in the MOS field effect transistor, or MOSFET. And when you hear about CMOS technology, it's talking about technology based on this MOSFET technology. And it works in a very simple way. So if you put a positive voltage on that grey gate at the top, it draws negatively charged electrons, coloured blue in that diagram underneath the insulator, and it connects 2 terminals known as the source and drain. And so only when the voltage is positive is the circuit connected. If you put a 0 voltage on that gate at the top, you won't have electrons and the transistor is turned off. And that is how a transistor is used as a digital switch. I mean, that is basically our society lives off that device, right? All of our calculations are based on that process. First demonstrated in 1953. The bipolar transistor came earlier in 1947, but it's the MOSFET that really has revolutionized society. So what we showed was that we could take the same materials and reduce the size of the electrons, number of electrons under that gate to just 1, and we use the spin property in order to encode the quantum information. And then it's just a matter of stringing these together. We showed the first quantum bit in 2014 in a paper in Nature Nanotechnology. The year after in Nature, we showed 2 quantum bits next to each other. That's the image in the middle. And what we're now doing is ramping this up to massive scale because we can use the same semiconductor foundries in order to make these quantum processes. And I mean, I think people are aware that really there was a book from a few years ago called Chip Wars, and it highlighted the fact that really now global geopolitics is in many ways determined by the chip industry and who has access to the most advanced chips, be it for GPUs and ultimately for quantum computers. And so the investments that are going in around the world are absolutely mind-boggling. You know, hundreds of billions of dollars being invested each year now to build new foundries around the world. Here in Sydney, we benefited, as I talked before, from really outstanding university-level fabrication facilities, such as AMP, Australian National Fabrication Facility. That's where we did all of the proof of principle. All those Nature papers I talked about were made on devices, were generated by devices made in Sydney at AMF. However, there's a limit to what you can do in a university clean room environment, and you really need high-end tier 1 manufacturing, and that's what we're now doing by getting our chips made in foundries, tier 1 foundries around the world. So coming back to the proposition I made about making compact, affordable quantum computers, this is a very simplified artist's impression. I'm afraid we can't show you our exact design because it's pretty confidential, but it gives a general idea. And so the black chip up at the top right represents the quantum processing unit that can have millions of quantum bits on it, made using standard CMOS manufacture. And then we see it integrated in a motherboard here with many other chips. These are classical CMOS chips that are used for controlling the quantum bits on the qubit, on the quantum logic unit, and also for reading out the signals. So on this one board that you could hold in your hand, we're envisaging quantum computers that have millions, and in fact, even up to hundreds of millions of qubits. And that makes it incredibly economical. So it means that using standard manufacture, we can make these chips. The foundries already exist to make them, and we are making them at the moment. And ultimately, we can produce an overall quantum computing system that is just a few square meters in total area. So visualize there on the right, most of those racks of electronics are actually classical processing units, GPUs and ASICs that are used in order to do the quantum error correction. All of the quantum processing is actually happening inside the the rectangular prism, which is a cryogenic rack-based cryostat where the quantum processor unit lives. And so that is our vision for fault-tolerant quantum computers. We're going to be releasing the first one in 2029 commercially, and we're looking for systems up into the millions in the early 2030s. I'd like to compare that to some of the competing technologies that are out there. So this is an image taken from PsiQuantum's website showing the facility that they're looking to build in Brisbane. And I want to first say that the PsiQuantum team are an outstanding team, really outstanding scientists and engineers. Jeremy O'Brien, who's the CEO, did his PhD at UNSW in the 1990s in what became the Centre for Quantum Computing. And what they are doing using single photonics is really impressive, and I have no doubt that they will be able to make quantum computers with this technology. The challenge, though, is that those systems are very, very large. So the image here, that facility being built near the Brisbane airport, which is nearly 100 metres on a side, contains huge crates of the photonic structures and all of the cooling to make the single photon detectors. And you can see a cryogenic plant that is used to pump liquid helium through that system. So the total cost of that, clearly of order $1 billion or so dollars in order to make, potentially higher. So I see no physics reason why this can't be built, and I think that you need to go out and do things for the first time. What we are looking to at Diraq, though, is to make the equivalent system so much more compact and so much more energy efficient. So it's not that our quantum computers are better quantum computers. The point is they're way, way smaller, they're way, way cheaper, and way, way more energy efficient. And so what that means is the cost per calculation that we have is way, way lower than those competing technologies I showed before. I just gave you the example of photonics, but in essence, all of those competing technologies either have the problem of physically large qubits, which mean that you can't get so many into a cryogenic system, or they have to operate at such low temperatures that you can't integrate the classical electronics. That's the case for supercomputing, for superconducting qubits. Or in the case of neutral atoms and ion traps, you need so much integrated laser technology that it creates some serious challenges. So look, conscious of the time, I want to wrap up in the next 5 minutes. I'm stealing an extra 5, sorry. So I just want to go over a few of Diraq's recent technology demonstrations, and I'm going to flick through these quickly. Firstly, we've developed a really critical relationship with the world's largest R&D CMOS foundry, IMEC in Belgium. This IMEC is an amazing place. Many tens of thousands of scientists and engineers, and they do all of the next generation chip technology for all the major chip makers in the world: TSMC, Intel, Global Foundries, Samsung, and many others. All of the next generation integrated circuits get designed at IMEC, and we are now making our quantum bits at IMEC. This just shows up in the top middle one of the first chips that we've made. This is a 12-qubit chip, but we now have designs over the next 12 months to increase that number very significantly. Can't release the exact number, I'm afraid. We're not releasing that publicly just yet, but it's a significantly high number competitive with our international competitors. And also, just over the last year, on qubits that have been made at IMEC, this is manufactured on 300 millimeter silicon wafers. That's the standard manufacturing unit in the CMOS industry. We've demonstrated the performance of our CMOS qubits at the levels required for quantum error correction. I mentioned before that you need to do error correction. In order to even be in the game for that, the qubits themselves need to have low error rates below about 1%. And we've demonstrated these low error rates or high fidelities of above 99% with these qubits made from IMEC. And we have another paper coming out in Nature in a few weeks together with IMEC showing that. So looking forward for our company, the first 3 years of the company has really been transferring our technology between 2022 and 2025 from a university environment into a foundry manufacturing environment. The next 4 years are really crucial for us because that's when we're going to ramp the qubit numbers up into the tens of thousands and to create our first commercial system. And we're targeting a system that will definitely be able to exceed supercomputers, albeit for a relatively limited range of product applications. And those will be designed for full commercial sale with that footprint I showed before. And then from 2029 onwards, that's when we're looking to push that qubit count up into the many millions of qubits. So we're looking to be in the millions around about the early 2030s. Another important relationship that our company has is with DARPA in the United States. I think people know DARPA, US Defense Advanced Research Projects Agency, developed a few minor things like the internet and GPS satellites. They are now embarking on a huge program, multi-billion-dollar program, to support companies who are developing full-scale quantum computing. And I'm proud to say Diraq is one of those companies. Should also say Silicon Quantum Computing here in Australia is another one. So we have 2 Australian companies out of 17 that were just selected globally. This program really is amazing. We're working with some great partners. So Diraq is leading our program with DARPA. We're working together with Emergence Quantum here in Sydney, I mentioned earlier, and also Riverlane in the United Kingdom, which is the world's largest quantum error correction company. And this photo is really just to remind me about the Nature paper that came out today together with Emergence Quantum. So Emergence Quantum is a new startup led by the gentleman on the left there, Professor David Riley and Tom Oakey. The guy in the middle, who's a little bit younger than us all, is a gentleman called Sam Barty. He did his PhD with David Riley at the University of Sydney. And the final thing he did for his PhD was he took a classical CMOS chip that had been developed by David's team, now Emergence Quantum, and combined it with a Diraq qubit chip and in one module showed that we could connect the two and use the classical chip to control the qubit chip. And the reason that this has just come out in Nature is because up until this point, in order to control the quantum bits, you had to run cables down from room temperature. So if you've seen those pictures of those refrigerators with all these cables, often called a chandelier type arrangement, those cables that send all of the control signals from the qubit chips up to room temperature. What we've showed here is we can now do that integration that I showed you, and that is at the heart of our technology. So this is an Australian-made success story out in Nature today. Please take a look. So our vision then for quantum computing moving forward is to use standard manufacturing. So no bespoke technologies. This is something that we can just get it made. So for example, you should think of Diraq as a company, something like an NVIDIA or an Apple. These are commonly called fabless companies because the fab is done in foundries outside the company. And the real value add is in the engineering of putting it all together and assembling it. And that's what we want to do in Australia. We want to do the advanced manufacturing here in Sydney, putting all this together and getting massive value add on the components that we put together. The chips could maybe in a variety of foundries. I will mention, though, that out in Western Sydney, we've got a new facility, the Advanced Manufacturing Research Facility. I know that state government here's been involved in setting that up. And we're looking at using that to package these chips together. And we think this is an amazing opportunity for Sydney and for Australia. So ultimately, we see quantum computing enabling all of those breakthroughs I showed before, designing new drugs, helping the energy transition. And ultimately, we see our quantum computers filling up data centers all around the world because they're compact, they're low energy, and ultimately, these will be cloud-accessible systems available to research groups and companies all around the world to generate those $1 trillion of revenue. So with that, I'll thank you for your attention. Please do follow us on LinkedIn, and happy to take questions. Thank you.
Thanks, Andrew. That was really great. And I have to say, the beginning bit, the explanation of qubits, is the most accessible one I've ever seen.
Oh, thank you.
Actually, so that was really good. We are open for questions.
I've got one over here.
Yep.
Oh, thank you. Hi, Christina Kabala. Thank you very much. That was really fascinating, and congratulations on your successes. It's very impressive. I had no idea we were so advanced. But speaking of advancement, with all of the speed and the power the quantum computers will be having access to, could I get your input on the risk side of quantum computing and security for the individual and for, across the board? It's not going to take a lot of imagination to imagine all of our passwords and our codes being broken. There's already a lot of cowboys out there looking at a quick buck. Mm-hmm. Could I get your input and your thought process on that, please?
Absolutely. All right, I'm going to hopefully put your mind at rest a bit because it turns out that, so what our questioner was referring to is the fact that it is one of the first applications of quantum computing that was ever envisaged was based on an algorithm designed by a gentleman called Peter Shaw from Bell Labs. He showed that a quantum computer would be able to much more efficiently find the prime factors of a large composite number. And that problem is at the heart of all public key cryptography that we use to keep our credit card information and other things safe. So it is true that quantum computers will be efficient crackers of public key encryption methods. However, the good news is that there are quantum hard codes. And in fact, a couple of years ago, under the previous US administration, Biden administration, a government directive was given to all US government agencies and departments to bring in quantum hard codes for the protection of all of their data. And so these codes are available, and there are companies that now will sell you services, including some here in Australia, that will give you access to quantum hard codes that you can use. Now, that doesn't protect data from the past, and so certainly people who are harvesting data now, that will be a risk. But looking forwards in terms of protecting information moving forwards, definitely we have the mechanisms to be able to protect against quantum computing attacks. Nevertheless, definitely governments are very interested in this for accessing information that is not properly protected or indeed harvested from the past. And it is one of the reasons why quantum computing is on the Defence Strategic Good list, because this will be a strategic technology for the future.
Got a microphone?
I think I can just...
Yeah, but everybody else, nobody else can hear you,
Yeah.
that's all.
Andrew, that was phenomenal. I've sat through many quantum computing classes during my Masters of Engineering, but that was very accessible. Thank you. Every development has a risk. You have a 29 plan and the 30s plan from few thousands to million plus. What are the major risks you foresee that would derail that plan?
Yeah, look, that's a very good question. And what I would say is that venture capital is called venture capital for a reason. It has risk, and any transformational technology that is, and certainly that become much more transformational in quantum computing, has risk in it. And all of the companies that are developing quantum computing technology all have their major challenges. Now, the major risk that we have as a company is there is a lot of engineering that has to go into designing those chips, and particularly to manage the thermal loads across those chips. I think everyone knows that your phone gets hot when you use it too much. Those chips heat up. And so it requires very, very careful engineering design in order to ensure that the thermal dissipation on those chips, on the classical chips, doesn't overheat the quantum chip. In fact, that was one of the big results about this Nature paper that I just mentioned, the fact we were able to put the classical chips so close without it heating our quantum bits beyond the level that they couldn't operate. So the thermal management and the design of that. The other thing I would say, and this goes for any quantum computing technology, quantum error correction is one hell of a complex thing, and it requires actual phenomenally large data rates between the quantum processing unit and the error correction units. And that's why, I showed you those 2 racks. Those are powerful racks of GPUs to do the quantum error correction. And getting all of that synchronized is a significant engineering challenge. I think one thing to recognize is that the sort of computers we use today have been developed over 70 years. And over that period, greater efficiencies and integration technologies were developed, and protocols, efficient protocols to run them, and engineering methodologies to design them. We're trying to compress all of that into around a decade. And that means we need to spend a lot of money on an engineering team and know-how. So that is the risk. It's in the engineering design. You won't be surprised to say we obviously have a very, very sophisticated systems engineering design program within our company. It's one of the things that DARPA are actually looking at with us and what they want to be convinced about. It's something that also provides some great opportunities for us compared to competitors, because a lot of the technologies that we have to bring up are already out there. So, for example, we can use standard computer-aided design tools to design our chips. Okay, so for example, we partner with companies in the US like Synopsys that have electronic design tools.
Let me just do the last question as a kind of follow-up, right, which is too often the case that we have been really good at developing technologies here. Photovoltaics comes to mind, but we've never really reaped the economic benefit. How do we get this one right?
Very good question, Hugh. Thank you.
I wanted to end on an easy question.
Is that a Dorothy Dixer, I believe it's called?
Is it?
I can say one thing at the moment for our company is that, we've raised 50 million in venture capital. The majority of that is actually offshore funds, not Australia. We had great support from some Australian, so Main Sequence Ventures have been strong supporters, Uniseed and Unisuper, Taronga Ventures, Coac Capital. and the University of New South Wales. No, but still the majority of our investments have come from overseas. And you know, one of the reasons, just one, that we set up in the United States is because the biggest venture and equity markets are in the United States. So there is quite a lot of pull to want to move us overseas, and we obviously see this for a lot of Australian companies. So I think that you know, this is where governments do have to step in and make appropriate investments to provide an attractive enough environment for companies like Diraq to want to stay here in Australia.
Good. Okay. Good. Thank you very much, Andrew. Appreciate it. We have various things here.
Thank you. Fantastic. Thanks very much.
Thanks very much, Andrew. It was a fantastic talk. Just to remind everyone, our next talk is on the 13th of August, which is National Science Week. And consequently, we've got a special talk from Jodie Rowley from the Australian Museum on Frog ID, the power of community engagement and conversation. So we look forward to seeing you again in August. Thanks very much, everyone.